very much, Elizabeth. It's really a great pleasure to give this talk. It's my first scientific online talk since the world went into chaos mode. I want to thank, before I begin, of course, the organizers of the workshop to give me this opportunity, and all of you for joining live, and those of you who will watch the recording later, thank you for that as well. The talk today will be about some variants of the Blaschke-Santaló inequality. So let me begin by recalling the classical Blaschke-Santaló inequality, going back, of course, to Blaschke and Santaló, and the equality conditions as they have been written on this slide were only settled by Petty later on. So the inequality states that the volume product of a convex body K in Rn and its polar, let's say, with respect to the Santaló point of the body, is maximized by ellipsoids. So my notation for a statement like this, so when a functional is maximized by a certain class of bodies, will be this. So this reads as the volume product is maximized by ellipsoids. And equality here holds if and only if K is an ellipsoid. And just to remind everyone, basically, or to fix the notation, what I'm writing here for polar bodies. So for a convex body with non-empty interior in Rn and an interior point K to the power x will be the polar with respect to the point x. In the following, I will often write K star instead of K to the power 0, which is the origin. So K star will always mean polar with respect to the origin, and the K with a bold S will be the polar with respect to the Santaló point, which is determined by being the unique point which minimizes the volume of the polar body with respect to a point in the interior. Okay, now most of you, or all of you, of course, know the Blaschke-Santaló inequality already, and all of you who know it also know that it is an affine invariant inequality, which means it doesn't change if you translate K or apply a non-degenerate linear transformation to K. So an inequality like this I will refer to as an affine isoperimetric inequality. And inequalities like this are often said to be more powerful than their Euclidean counterparts. And in the case of the Blaschke-Santaló inequality, one example of such a Euclidean inequality that is a consequence of the Blaschke-Santaló inequality is Urysohn's inequality. And I want to spend a little bit of time explaining this in more detail. So we have the classical Urysohn inequality, which is an inequality between the mean width of a convex body K, which I have recalled down here. So the mean width is, well, a mean of the width in every direction of the body, which can be written as a projection onto the length of one-dimensional projections averaged over all the directions and then suitably normalized. So you take all the widths in different direction and you take a mean of those. So that's the mean width. And we compare it to the volume raised to the right power so that this becomes scaling invariant. And the statement of Urysohn's inequality is that this ratio is minimized by Euclidean balls with equality if and only if K is a ball. Now, plugging in the definition of the mean width here, we can rewrite this inequality a little bit by writing this mean of the lengths of one-dimensional projections on the left-hand side, and then the volume raised to the power 1 over n on the right-hand side. And I'm suppressing here a constant, which I indicate by this twiddle. So whenever you see an inequality sign with a twiddle, this just means there's a constant here that's easily computed by plugging in, for example, the equality conditions. So that's, again, just Urysohn's inequality. And I think it was first noted by Erwin Luttwak in the 70s that Urysohn's inequality can be improved by replacing this L1 mean that we have here in the definition of the mean width by an L minus n mean. So if you just follow along, you see the only thing we changed here was that we replaced the 1 here by a minus n and the 1 outside by a minus 1 over n. And then by Hölder's inequality, this quantity will be bigger than the mean width, which means this inequality implies the Urysohn inequality. And something unexpected also happens. This quantity now becomes an affine quantity. And so I think I have this as a remark. So this is again an affine isoperimetric inequality. It is stronger than the Urysohn inequality. I mentioned this already in the sense that you can estimate this against the mean width simply by applying Hölder's inequality. And the inequality that we have here on the right-hand side is a consequence or a weaker form of the Blaschke-Santaló inequality. It coincides with the Blaschke-Santaló inequality for centrally symmetric bodies, but for asymmetric bodies, this is a weaker form. And I actually want to spend a little bit more time with this weaker Blaschke-Santaló inequality because you can reinterpret it as an inequality for difference bodies. And here's the recollection of what the difference body of a convex body is. So we have a map, capital D, from convex bodies in Rn to convex bodies in Rn, defined with the help of the support function of a body. And the support function of the difference body of K is simply this length function of one-dimensional projections. So here you see the difference body of a simplex. And the reason I'm introducing those or recalling those is that the inequality we saw on the previously slide by Erwin Luttwak, that was this L minus n mean, is the same just by using polar coordinates, volume, so expressing volumes in polar coordinates. The inequality from the previous slide is exactly the same as this volume inequality for polar difference bodies. So my notation here is that D star K is the same as first taking the difference body and then taking the polar, as I explained, with respect to the origin. So these difference bodies, of course, they appear in various places in geometry, and they have essentially two characterizing properties, as we will see in a second. First of all, they are what I would call Minkowski additive. So a map from convex bodies to convex bodies is Minkowski additive if, well, it satisfies this additivity where the plus is just the usual Minkowski sum. And clearly the difference body map is Minkowski additive. And the difference body map also commutes with general linear transformations. So
sorry, why do you call it difference body? As far as I know, it is a projection body, isn't it?
No. So I'm calling this, so I go back, the difference body because dk is the same as k plus minus k, where minus k is the reflection at the origin. The projection body is the one where you calculate n minus one dimensional volume of
thank you.
hyperplane projections.
Thanks.
No problem. Okay, so we had these properties, Minkowski additivity, commuting with GLN transforms, and also the difference body map is translation invariant. And then in, also I would call it classical result of Rolf Schneider from the 70s says, if you have such a map, then it must be a multiple of the difference body map D. Schneider actually, in this paper from 1974, did not work mainly on GLN compatible or affine compatible Minkowski additive maps, but considered what he called Minkowski endomorphisms. So a continuous map is called a Minkowski endomorphism, and this these are the Minkowski endomorphisms from the title of this talk. So if the map is Minkowski additive, like we saw before, if it is translation invariant, and here's the difference to what we had on the previous slide. So phi is not assumed to be compatible with general linear transformations, but only with rotations. So phi should commute with the group SON. Now, the difference body map is an example of such a Minkowski endomorphism, but now, since we only assume commutativity with rotations, we have much more maps, and we will see that these Minkowski endomorphisms actually form an infinite dimensional cone. So there are lots and lots of those. I want to give you two more examples, quite simple ones, or at least the first one is very simple. So the first one, which I call capital W, is defined by mapping every convex body to a ball, but the radius of the ball, so the Bn is the unit ball, the radius of the ball depends on the mean width. So every convex body is mapped to a ball of radius mean width of k. So this would be an example of a Minkowski endomorphism. And we have what's called the first projection body map. So if you're familiar with the usual projection body map, Minkowski's projection body map, so there's a Steiner formula for this classical projection body map, and one of these terms that appears there is this first projection body operator, but you can define it just like this. So the support function of pi1 of k is now the mean width of k projected onto the hyperplane orthogonal to U. Okay, so this would also be a Minkowski endomorphism. And as I said, there are many more examples, and the reason I chose this is the following. So let's assume we have a convex body with non-empty interior in Rn. Then we have already seen that the difference body map satisfies this Blaschke Santaló type inequality proved by Ludwig. If you think a little bit about the definition of the capital W, you will see immediately that Urysohn's inequality can be expressed as a similar inequality. So this is also a volume product of the map W polar of K. And this is exactly Urysohn's inequality if you plug in the definition of the capital W. And Ludwig proved in 1993 that also the pi1 polar, or the pi1, satisfies a similar inequality. So we have these volume product inequalities for polars of Minkowski endomorphisms. So these three Minkowski endomorphisms. And in one of my very first papers, I was considering these Minkowski endomorphisms, and when I think it was in my very first meeting with Erwin Ludwig in 2006, he suggested the following problem. So consider a Minkowski endomorphism, and let's say it's not trivial. So there's a trivial one here, which maps every convex body just to the origin. So we are not interested in that. For this one, well, these inequalities don't make sense. So we exclude this one. So let's say you have a non-trivial Minkowski endomorphism. Does it follow that this volume product of the polar volume of phi, essentially with the volume of K, is always maximized by Euclidean poles?
Franz, may I ask a question? This was, if you consider the Steiner point, is it a non-trivial Minkowski endomorphism? It is just a point, so maybe it is also trivial?
Yeah. So the Steiner point is not translation invariant.
Okay, thank you.
Yeah. So the Steiner point will appear soon in a couple of slides, and it plays actually an important role of some new phenomenon that we see. So I come back. So thanks for mentioning it. But it doesn't fit in yet into the scheme. Okay. So yeah, what I wanted to say and what I mentioned already is that there are lots and lots of these Minkowski endomorphisms. So where do you start when you want to tackle a problem like this? You got to get more information about these classes of maps. And luckily, this was already done in the past. There have been several papers, and I'm just mentioning here two. So there was this Schneider paper from 1974 that kind of was the first introduction of those, and he obtained lots of results already. And then this was picked up by Kiedelen in the early 2000s. And the statement that you read now is actually from Felix Dorek, a former PhD student of mine, and was published in 2017. And it states that when you have a Minkowski endomorphism, then there exists a signed measure, which is SON minus 1 invariant on the sphere, and which has center of mass at the origin, such that the support function of the Minkowski endomorphism of K is always the support function of K convoluted with mu, where this convolution is a spherical convolution. So here the support function is considered as a function on the sphere. And this spherical convolution is induced from the Lie group SON, where you have a very natural convolution of functions there. And I don't want to go into the details here. Let's just say there's a natural convolution of functions on the sphere, and this is used here. Okay, so we know that we have this kind of nice formula, but unfortunately, to this day, we still don't know which measures exactly generate Minkowski endomorphisms. We know that whenever you have one, you have a representation with a unique measure mu, invariant and center of mass at the origin like this, but we do not know exactly which measures appear.
Franz?
Yes.
Sorry, but do you know which measures appear for the three examples that you mentioned?
Yes, of course, yes. For all the well-studied examples, the measures are clear. So for the difference body map, the measure mu is a discrete measure concentrated on 2 points. For the W map, which was the mean width map, this is just spherical Lebesgue measure. And for the projection body, this is concentrated on the equator of the sphere. So this is all well known. And in fact,
and what happens? Sorry, and what happens if you can consider mu on k-dimensional equators then? So that would be everything in between.
This you can't do because you need SON minus 1 invariance. So this must be an SON minus 1 invariant measure here. We do know a little bit more if we add an additional assumption, and this is why the name Kiedelen appears here. So Kiedelen had a version of the statement from before, but this was refined by Felix Dorek. But Markus Kiedelen proved that the Minkowski endomorphism phi is monotone if and only if. So here we have a complete characterization if and only if the measure mu is non-negative. And monotonicity means just monotonicity with respect to set inclusion. So what you would expect. So K in L implies phi K is in phi L. So monotone Minkowski endomorphisms are very well understood. They are all of this form coming from convolution on the sphere with a non-negative measure. Okay, and using this classification result, Georg Hofstätter, a current PhD student of mine, and myself were able to give a quite satisfactory answer to the problem that I posed before. Whenever you have a monotone Minkowski endomorphism, then this volume product of the polar volume is always maximized by Euclidean bars. And if the map is not a multiple of the difference body map, then equality holds only if and only if K is a bar. So for the multiples of the difference body, of course, you have here equality if and only if K is an ellipsoid. So, but we have already seen D is special here. It is the only one compatible with general linear transformations. All the three inequalities I showed you before, so Urysohn's inequality, the Luttwak's Blaschke Santaló inequality for polar difference bodies, and the what I call Luttwak petty projection inequality for pi1. These are all special cases here, but this is an infinite dimensional family of inequalities if you want, because any non-negative measure on the sphere which has this invariance property induces such an inequality. We had a preliminary version of this result with Astrid Berg, which appeared last year, but this was for a much smaller cone of monotone endomorphisms and was derived from earlier results with Christoph Haberl. And so this is really a much more satisfactory result, because the one with Astrid was really not what we expected or wanted. Okay, so we have seen that the Blaschke-Santaló inequality, the classical one, is stronger than the Urysohn inequality. And we see something similar here. The Urysohn inequality is a special case here. And in fact, we showed that, in a sense, the Urysohn inequality is the weakest one among them. And the Blaschke-Santaló inequality, which you see here, this is just Blaschke-Santaló, so volume of K polar compared with the volume of K. This is the strongest inequality. It's not really included here, but you have the one for the difference body map here, which is included and which is basically the strongest one among even Minkowski endomorphisms. Okay, so this is one remark I wanted to make. The other one, or the story goes on. Of course, if you have this result for monotone, you might ask, do you need the monotonicity assumption, or can you get rid of this? And there's a slightly larger class of Minkowski endomorphisms that's also been studied and is quite well understood. And these are the weakly monotone ones. And here is their definition. And here comes the Steiner point that was mentioned by Boas before. So a Minkowski endomorphism is called weakly monotone if the usual monotonicity holds, but only for those bodies whose Steiner point is at the origin. So here's the definition of the Steiner point. That's a vector valued integral that you have here. So you integrate the values of the support function against just the vector u on the sphere, and you normalize correctly. And for those bodies whose Steiner point is at the origin, we ask that this monotonicity property is satisfied. Now, something that came as a bit of a surprise for us was that it turns out that there is a quite simple example of a weakly monotone Minkowski endomorphism for which this volume product is unbounded. So this example is basically a modification of the identity map. So note that the identity is obviously Minkowski additive. It commutes with SON, but it's not translation invariant. So you can use the Steiner point to modify the identity map in such a way. So you just translate K by its Steiner point, then this will be a Minkowski endomorphism. It won't be monotone, but it will be weakly monotone, obviously, just by the definition. And it turns out that the volume product for this modified identity is unbounded. And so here's the idea. This is actually a computation, and I'm not going to do the computation for you, but I'm going to give you the idea of the computation in 2 dimensions. So this result is true starting from dimensions n greater or equal to 2. So what I've plotted here is a triangle. So the vertices are chosen in such a way that it has always volume 1. And the orange part that you see here is the so-called Santaló region of K that was systematically investigated by Mathieu Meyer and Elizabeth, let's say in a paper 1998. And for this simple body, for this simple triangle, you can actually compute this exactly. You can compute the location of the Santaló point, which is the green point, and the location of the Steiner point, which for this triangle, they do not coincide. And then what you do is you make this triangle a little bit flatter, in a sense. So you move the vertices in such a way that you keep volume 1. And then you notice that the Steiner point is leaving the Santaló region of K, while the Santaló point is, of course, staying right at the center of the Santaló region if you want. And if you make this triangle more and more flat, what happens is not just only the Steiner point leaves the Santaló region, but it gets so close to the origin that when you take the polar with respect to the Steiner point, then the volume of the polar body will blow up, and you get the result from the previous slide. So apparently there's no way to extend the result that we had for monotone Minkowski endomorphisms, a very satisfactory family of inequalities, to merely weakly monotone Minkowski endomorphisms. And not just because there is one example which has unbounded volume product, but there's another unexpected consequence for us about the existence of this unbounded example, namely that there exist lots and lots, as we will see in a minute, lots and lots of weakly monotone Minkowski endomorphisms for which this volume product is maximized by bodies which are different from Euclidean balls. So this is unexpected for me because I have been studying these isoperimetric inequalities coming from maps that have certain additivity properties and are compatible with rigid motions for a long time. And usually I expect them to have as extremos Euclidean balls. And here we have, many examples now where the family includes operators or maps which lead to extremos that are different from balls. And the proof is quite simple. So I'm going to give you actually the proof of this little corollary. We start out with a non-trivial monotone Minkowski endomorphism. So remember that for the monotone ones, we had the the inequality that this volume product is always maximized by balls. To make formulas a little bit nicer, let's assume that we normalize the map such that the Euclidean unit ball is mapped to the unit ball. Okay, balls are always mapped to balls, so this is really just a normalization of the map capital sigma. And now we define the map capital phi, which we claim is maximized, for which the volume product will be maximized by bodies different from balls, as follows. We take a convex combination of this sigma and the modified identity map, which was the one that yielded this unbounded volume product. Okay, so the lambda we will choose a little bit later. For now, let's just take lambda anywhere between 0 and 1. Then, so the phi, because of our normalization of the sigma, and because J maps the Euclidean ball also to the Euclidean ball, phi will map the Euclidean ball to the Euclidean ball. So notice that the volume product is, of course, scaling invariant. So this means that phi of any ball, independent of the center and independent of the radius, will be the volume of the Euclidean unit ball squared. Okay. But what do we know about the volume product, volume of K and volume of phi polar K? Well, phi is obviously containing lambda sigma of K. So phi of K is larger than lambda of sigma K, because we drop this part here, right? So if you take polars, we get the first inequality here. So the lambda I've taken out from the sigma. So just by definition of the phi, we get this first inequality. And then for the volume product that we have now here, we just apply the theorem for the monotone Minkowski endomorphisms, which says that this is maximized by balls. And so we get this constant here. So we see that this volume product is bounded from above by a constant, which means the supremum of this volume product exists. But as lambda gets closer and closer to 0, we are closer and closer, we are moving closer and closer to the J, and the J has unbounded volume product. So this supremum can be as large as we want by letting lambda just be smaller and smaller. All right. So we know that the supremum exists and can be arbitrarily large. So in order to prove our corollary, what remains is to show that this supremum is actually attained and is a maximum. And for this, we need a little bit extra regularity for the sigma. So we had this theorem before that they are all coming from convolution with measures. And this extra regularity here is an assumption that, let's say, this measure has a positive density. So the measure is non-negative already, and we wanted to have a density, strictly positive density. So this is not asking very much. And then you can quite easily show that the supremum is actually a maximum. And so I give you one concrete example that I like quite a lot. So let's take, for the sigma, we take the W map, which is this very easy map, mapping everything to the ball with radius mean width. And we choose a lambda suitably. So you have many choices here. I chose lambda to be 1/2 here, which is fine. Then the volume product becomes this thing here. So when you look at this, this is just a translate of K/2. So 1/2 of K translated with respect to half of the Steiner point, and then a parallel body of that. So K keeps its form, and then you take a parallel body where the radius of the parallel body depends on the mean width of K. So that's only I would say a slight modification of K, but this thing will not be maximized by Bors anymore. And I have no idea by what the extremal is here. I don't know if they will be, if this will have unique extremizers. And if you plug in here a parameter lambda, then I don't know how the family of extremizers changes as you change lambda. So there are lots of questions only pertaining to this particular example here. Okay, so my time is almost up, but I have a few more things I want to say, namely that it has, of course, been a big topic over the last 2 decades, probably, to consider also functional versions of well, all kinds of isoperimetric inequalities, geometric inequalities, and of course, very famously, there's a functional Blaschke-Santaló inequality that for even functions was first obtained by Keith Ball in his PhD thesis, and then in the form that I've stated it here by Shiri Artstein, Boas, and Vitali. It can, well, be stated in different ways, but I've chosen a quite simple one. So essentially it says the integral of a log-concave function on Rn against the integral of its polar is maximized by this constant with equality if and only if f is a Gaussian. And polarity, of course, for log-concave functions is related to the Legendre transform in this way. I do not want to spend so much time explaining this here. Georg Hofstätter has given a talk last week for the conference in Bremen, the online conference in Bremen. His video about Asplund Endomorphisms is still online. So if you want to know more about these last 2-3 minutes that I'm speaking here, please go to his video, which is 20 minutes, and he spends more time with the details here. Let me just say that I'm well aware that there are more general versions of this functional Blaschke-Santaló inequality and new versions by Elizabeth, different proofs. For us, interesting is that this functional Blaschke-Santaló inequality is again stronger than a functional analog of the Urysohn inequality by Boas, Vitali, and this was first observed by Liran. And also let me mention that you can recover the geometric sharp Blaschke-Santaló inequality by putting in this function. Yeah. Okay, now what I want to do is generalize our notions to this setting of log-concave functions. We have to add a little bit of a technical extra condition, namely coercivity. So instead of working with convex bodies, we work now with log-concave functions which are coercive. And coerciveness is here, just means that it decays to 0. For convex bodies, for the space of convex bodies, we have the Hausdorff metric. For this space, we induce it with a topology. We endow it with a topology induced by epiconvergence. We have support functions of convex bodies that determine the body uniquely. We have support functions of a log-concave function, which is a convex function that determines the log-concave function uniquely. It's the Legendre transform of minus log f. And with this help, I can very conveniently state this, the addition that we're using. So for convex bodies, we have Minkowski sum. And for log-concave functions, you just take Asplund sum. Asplund sum is usually defined in a different way, but it's very convenient to define it with the help of these support functions. And this is all we need to just replace Minkowski endomorphisms by Asplund endomorphisms. So these are exactly now what you would expect. They are Asplund, additive, translation invariant, and commute with rotations. And I forgot to mention that coerciveness is really necessary here, because if you don't assume coerciveness, the space of just log-concave functions, upper semi-continuous and proper, will not be closed under Asplund sum. You know, you leave the space, and so coerciveness really implies that your space is closed with respect to this addition. Okay, and then we had two results. One is kind of a generalization of the result of Kiederlen. We have this very large family of monotone Asplund endomorphisms generated by an extension of the spherical convolution that I'm not going to explain. And this spherical convolution extension has the property that if you plug in indicators of a convex body, then the Asplund endomorphism applied to the indicator will be the indicator of the corresponding Minkowski endomorphism. So these Asplund endomorphisms, as defined here, they are very closely related, and well, they are a functional extension of the Minkowski endomorphisms that we considered before. And we have a corresponding functional versions of our inequalities. So everything looks the same as for the classical inequality. For the functional Blaschke Santaló inequality, you have the integral of f, and then the integral of the image under the Asplund endomorphism polar, and we have a complete description of equality cases. And two more small remarks, and then I'm done. If you plug in indicators here, you get the geometric inequalities for Minkowski endomorphisms in an asymptotically sharp form. If you take mu, the measure that generates the Asplund endomorphism, to be normalized spherical Lebesgue measure, this will give you a functional analog of the Urysohn inequality, a new one, which is stronger than the previously obtained versions. And I was a bit fast in the end, but I hope it was still manageable to follow, and I thank you all for staying with me. Okay.